So, what do vending machines and your GPS have in common? It sounds like the start of a bad joke, right? But the answer actually gets right to the heart of a huge idea in math. Think about it. With each one, you give it a specific input, a button press, or your location, and you get one single, predictable output back, your snack or the fastest route home. This simple, reliable input-output system, well, it's pretty much everywhere.
And that system, well, in the world of math, we call it a function. So today, we're going to pop the hood and explore how these simple but incredibly powerful mathematical machines really work.
Here's our game plan. We'll start with the absolute basics. What is a function? Then we'll learn how to classify them, kind of like a field guide. We'll see what happens when we chain them together or try to run them backwards. We'll use that knowledge to solve a classic trig puzzle, and finally, we'll talk about why this all matters in the real world.
All right, let's get right into it. Let's start with the most fundamental question of all. What exactly is a function?
At its core, a function is just a rule. But it's a rule with one super important non-negotiable condition. For every single input you feed into it, you get exactly one output. Not two, not zero, just one. That's it. That one rule is the bedrock that makes functions so predictable and so powerful.
Okay, so to talk about this stuff properly, we need a little bit of vocabulary. The set of all the things you're allowed to put into the function, that's the domain. The set of all the possible things that could come out, that's the codomain. But here's the key distinction. The set of outputs the function actually gives you is called the range. So the range is a part of, or sometimes all of, the codomain.
Now, if you're looking at a graph and you're not sure if it's a function, there's a fantastic little trick called the vertical line test. It's so simple. Just imagine sliding a vertical line across the graph. If that line ever touches the curve in more than one spot at the same time, bam, it fails. It's not a function. Why? Because that would mean one input has two different outputs, and that breaks our number one rule.
Okay, so we've got the basic definition down. But here's the thing. Not all functions are created equal. They have different behaviors, different personalities. So now, we're going to become function spotters and build a field guide to classify them.
The first big question we ask is, do inputs have to have their own private output, or can they share? A one-to-one function, the technical term is injective, is strict. Every input gets its very own unique output, no sharing allowed. But a many-to-one function is totally fine with different inputs all leading to the same output. You know, like how y equals x squared gives you y equals 4, whether you plug in 2 or -2. And trust me, this distinction is going to be a huge deal in a few minutes.
And hey, guess what? We have another graphical test for this. It's called the horizontal line test. Same idea as before, but this time if a horizontal line hits the graph more than once, it means multiple inputs share the same output, so it's many to one. See how that full parabola on the left fails? But look at the trick on the right. If we just look at half of it, it suddenly passes. Tuck that little idea away. It's important.
All right. The second question for our field guide is totally different. It asks, does our function actually use all the possible outputs available to it in the codomain? If it hits every single possible target, we call it onto, or surjective. But if there are some potential outputs left over that never ever get used, we call the function into.
So when you put these two classification systems together, you get these four basic personalities for any function. You can be one-to-one and onto, many-to-one and into, and so on. This gives us a really precise language to describe exactly how any given function behaves.
Now there's one specific combination here that's like this superstar of the function world. When a function is both one-to-one and onto, it gets a special name. We call it bijective. Think of it as a perfect matchup. Every input has its own unique partner output, and no possible outputs are left on the sidelines. This is the gold standard, and it is the absolute key to what's coming next.
Okay, so we're getting pretty good at spotting and classifying these functions. Now for the fun part. What can we actually do with them? First up, we can link them together in what's called a composition. The factory assembly line analogy is perfect here. You take the finished product from your first function machine, and you immediately feed it in as the raw material for a second function machine. It's a simple idea that lets us build incredibly complex operations.
But what if we want to go backwards? What if you have the output and you want to know for sure what input created it? For that, we need something called an inverse function. But as you might have guessed, there's a catch.
And here it is. This is the big rule. This is why we cared so much about those classifications. A function can only have an inverse if it is bijective. It makes perfect sense when you think about it.
If it was many to one and you tried to go backwards, how would you know which of the many inputs to go back to? You couldn't. It would be ambiguous. A bijective function guarantees a perfect, unique two-way street.
So let's put this big, important rule to the test with the classic puzzle that you've probably run into in a math class somewhere.
Let's talk about the sine wave. You know, that endless, repeating wave? If you hit that thing with the horizontal line test, oh man, it fails spectacularly. It's the very definition of a many-to-one function. So, according to our big rule, it shouldn't have an inverse. So how in the world does your calculator have an inverse sine button? What's going on here?
Well, the solution is basically a really elegant cheat. We can't use the whole infinite sine wave, so we don't. We make a pact. We agree to only look at one small piece of it, a specific section where the wave doesn't repeat itself. Inside that tiny restricted window, the function does pass the horizontal line test. It is one-to-one. And it's for that piece only that we can define an inverse.
And this right here shows why that little agreement is so incredibly critical. The order matters a lot. If you start with a number, take its inverse sign, and then take the sign of that, you always get your original number back. No problem. But if you go the other way, if you take the sine of an angle and then ask for the inverse sign, the inverse function can only give you back an answer that lives inside that special restricted window. It has no idea about all the other infinite angles that would have given you the exact same sign value.
Okay, so we've gone through all this injective, surjective, bijective, vertical line tests. Why does any of this stuff really matter in the big picture?
It matters because functions are way more than just squiggly lines on a graph. They are the language we use to describe the predictable rules of the universe. The laws of physics, the models of finance, the algorithms that run our entire digital world, they are all built on this fundamental idea of a reliable, predictable cause and effect relationship.
So yeah, functions give us this incredible framework for understanding the predictable systems all around us. But that leaves us with one last fascinating question to chew on. What about the things that aren't so predictable? What happens when we can see the inputs and we can see the outputs, but for the life of us, we can't figure out the function, the rule that connects them? Well, that's where the map ends, and that's where the real frontiers of science and discovery truly begin.